find all the points of self-intersection on the curve r equals 1 over theta. Okay, self-intersections. So this is where the curve loops around itself and sort of hits here, and maybe hits here and here. So find all these points. We want all of them. There might be no points. There might be tons of points. There might be infinitely many points. We need to find ways to express them. Okay, so let's hop on over. All right, so our curve is r equals 1 over theta. When we check for self-intersections, it's almost the exact same as checking for intersections between two curves, but in this case, the curve is the same. There's just a slight tweak that we have to do, which we'll get to in a moment. But first things first, always check for the pole. Is it possible for r to be equal to 0? Well, in order for 1 over theta to be equal to 0, you'd have to have, multiplying by theta on both sides, you'd have to have 1 equals 0. That's just not going to happen, right? 1 over theta is never equal to 0. You can see this with a quick sketch. Right, on like a theta r axis, never hits the r equals 0. So no, the pole is not on this curve. Okay, happens. What else could happen? And this is where we need to slightly change the approach when we're dealing with self-intersections. So another option is you have the same r value, but for theta values that differ by an even multiple of pi. Okay. So we set that up, but we remember k can't be 0. Because if k is 0, then this is 0, and you have 1 over theta is equal to 1 over theta, which, of course, it's true. That's always true. That's not a self-intersection. That's just saying this point is on the curve, and this point is still on this curve. So we want to solve for thetas and k values, specifically non-zero k integers, that make this true. All right, multiplying both sides. Right, it's doing what people tend to call cross-multiplication. You'll get something like this. You can cancel out the theta value, or the theta values. Right, subtract the theta values on either side, and you get 2 pi k must be equal to 0. Divide by 2 pi. K must equal 0. Well, that's exactly what we don't want to have happen. Right, so that also doesn't lead to any self-intersection. So this may sort of be a trick question where maybe this thing doesn't have any self-intersections, right? Maybe it's sort of just like a spiral that just goes around and around and around and never hits itself. You get lots of those with polar coordinates, right? So there is one other option, and that is that you get the same distance, but from a positive and negative r, and your thetas are shifted by an odd multiple of pi. So that is the other option. This time, we don't have any restriction on the k value, just any old odd multiple of pi, because there's no way that can be 0, and so it's no way that you're using the same theta value for each. Okay. So now, just as before, we can cross-multiply, so theta plus 2k plus 1 pi equals minus, don't forget that minus, theta. We can add the two thetas there. And we can divide by 2. We can bring this over to the other side as well. And we're going to get theta is minus, although you don't have to have that minus sign in there, because if you choose k to be a different value. So right now this is a negative odd multiple of pi. Well, if you choose k so that 2k plus 1 is negative, you can sort of absorb that minus sign if you really want to. Think about it for a moment. But divide by 2 to solve for the theta. Okay? So these thetas should give me a point of intersection where one you're getting sort of a positive r, and the other one is coming from a negative r, but you are plotting with theta values that are a half circle away, and so they do plot to the same point. Okay, so this is what's going to hold for any integer k. So there's the symbol for integers, k being any integer. And, if you want to write that out in words, go for it. And then what are the actual points? Well, the r values are 1 over theta. So we might say all the points of self-intersection are 1 over this sort of theta. And then, of course, this sort of theta here. Of course, 1 over a fraction, you'd get 2. So minus 2 over 2k plus 1 pi, and then minus 2k plus 1 pi over 2. So we'll say for all integers k. Okay. Great, perfect answer. Nothing, no notes really, but if you wanted to, as I was saying, you can absorb the minus sign by choosing different k values, right? If k equals 1, for example, you get 2 times k plus 1, you get 3 pi, so you get negative 3 pi by 2. But if instead you chose k is negative 2, you'd have negative 4 plus 1, you'd have negative 3 pi, and you'll get negative 3 pi by 2, and you can actually flip. For each k value that gives you a negative 1, you can find another k value that'll make the positive 1. And so if you had wanted to absorb that, if I was writing maybe a slightly nicer, neater answer, I would have probably found a way to realize that, if you're doing all k's, then, with 1 you get an answer of minus pi by 3, but with k equals negative 2, you get 3 pi by 2. And so you don't really need the minus sign in there. Oh, there we go. So that might be a cleaner answer, but they're both talking about the same set of points overall. Right? So there we go.